Hi, and welcome to my first ever video blog. This screencast is about using the Locator ID separation protocol, or LISP, to support cold migrations of applications between data centers. My name is Joel Knight, and I'm a systems engineer with Cisco. I work with customers in Western Canada. You can find my blog at www.packetmischief.ca, and you can also find me on Twitter at Knight_Joel. This screencast is part of a larger series on data center interconnects that I've been doing. This is the list of posts that I've done to date. You can find these at the URL on the screen there. Please post a comment or find me on Twitter. I'd love to hear from you and hear your feedback. So before we get into talking about cold migrations and how Lisp can support us in that, I want to set the stage for a little bit and talk about hot migrations and what hot migrations look like, and then do a bit of a compare contrast to cold migrations. So in a hot migration, by definition, we're moving an application and a server while it's online and still servicing users. From the user's perspective, they don't know that anything is happening with the application. They don't see an interruption in service. So the way that works at a very high level, user is accessing the application, platform administrator comes along, does a hot migration of that application to another location, and the user's traffic is then follows that application to the other location. That's a critical part to the success of a hot migration. Obviously, if users' traffic is impacted, then it's not such a hot migration anymore. So how do we ensure that that traffic is continuous, that that user's session is not interrupted as the application is moved from left to right here? Well, one of the ways is through straight layer 2 bridging. So we build a layer 2 trunk between the sites, and we bridge the VLANs where these applications and these servers are hosted between the sites. In essence, we're creating one larger network that spans two physical locations. So in that instance, again, once we migrate that machine over, or that virtual machine over, it doesn't really matter which location that user's traffic first hits, because it's all one big network. So in this case, traffic comes into the data center on the left. That data center knows that the MAC address associated with that virtual server is now located in the other site, and it's just a simple layer 2 bridging, switching operation to get that user's traffic from left over to the right site. Now, besides the inefficiency of this, what are the issues with this design? Well, as I said, we've created one large network that spans both locations. And we've done that by extending that layer 2 domain between the two sites. Layer 2 domain is equivalent of a failure domain in an Ethernet network. So what we've done here is created one large failure domain. Any sort of interruption, a physical loop, a loop that opens up in the network, misbehaved hosts, even things like unicast flooding and whatnot, unknown unicast flooding, they're going to propagate and touch the network at both locations. And in the worst case, consider a layer 2 loop, we're going to affect the network at both locations. So we've just undermined the redundancy and resiliency at the compute layer, at the storage layer, at the facility layer. We've undermined all that by having this network that has not been engineered to segment those failure domains and ensure that an issue at one site cannot affect the other site. Do not engineer your networks like this. An alternative approach is OTV, Overlay Transport Virtualization. So we know we still need that layer 2 adjacency. That is a requirement if we need to be able to deliver hot migrations of workloads. So how do we achieve that without taking on the risk of layer 2 bridging? So you'll notice in this example here, the two data center locations are not connected together with a layer 2 connection. The only connectivity between them is through this routed WAN service. So what we do with OTV brings up an overlay connection, which is basically just a stateless tunnel between the routers at each location. And this tunnel carries encapsulated layer 2 frames. So if we have, let's say, a hypervisor host in the data center on the left and another on the right, those two hosts actually see themselves as layer 2 adjacent. They don't know that OTV is playing a role here. They don't even know that there isn't a true layer 2 connection between the sites. But they know that when they put layer 2 frames out onto the wire, destined for the other hypervisor host, that they're able to connect in a layer 2 manner, if you will. So same situation here. We migrate application from one site to another. And again, doesn't matter which site the user's traffic comes in, the network knows where the MAC address lives that's associated with that virtual server and is able to pass those frames between the sites as necessary. So again here, user's traffic enters data center on the left. The network in that data center knows where the MAC address is for that virtual machine, and it sends the traffic across the overlay, which comes out the other side and hits the virtual machine. So we've seen here that one of the key enablers to hot migrations is some sort of layer 2 connectivity between the sites. We require that so that A, the user's traffic is able to be redirected as shown here, and B, so that we have the same IP subnet in both sites. Obviously, when we're migrating that virtual machine from site to site, the IP address of that machine stays constant. There's no change there. If we were to change that IP and yank its IP off of there, slap a new one on as the machine came up in the new site, that would not really be conducive to hot migration. Any user sessions that are active on that application or to that server would instantly be broken. So the IP stays the same as we move. And in order to facilitate that, we need the same IP subnet in both sides, which means we need to be able to exchange layer 2 frames between the sites as well. Now, another technical requirement for enabling hot migrations is the distance between the sites has its upper limits. And that really comes down to an issue of latency. So the latency between the host on the left data center or in the left data center, host on the right data center, has to be within a certain range so that they're able to perform that hot migration function, which in VMware world would be vMotion with Hyper-V, live migrations. In order for these hypervisors to perform that operation, the latency between the hosts has to be within a supported range. So usually you would see data centers, as shown in the example here, would be in fairly close proximity, probably in the same metropolitan area, lots of high bandwidth connectivity options between the two sites, and very low latency. The other aspect of this, which is not shown on the diagram, is the need to do synchronous storage replication between the sites. So in order for the VMDKs and the virtual hard disks belonging to these applications to be replicated site to site, the storage subsystem would typically do synchronous replication, and that has its own latency requirements with it as well. So that's all good for hot migrations for data centers that are close together. But what about the case where we have, say, a disaster recovery site that isn't in the same metropolitan area? It's in a different city, it's across the country or across the province or state. What about the case where we're trying to migrate workloads into the cloud, where the distance could be anything, could be short, could be long, and where we most certainly don't have that layer 2 connectivity. how do we achieve that workload migration um, and maintain reachability and simplicity in the environment? So quickly here, a high level look at cold migration. So slightly different scenario here. This data center would be a production data center, and then the other data center here, consider it as a disaster recovery site. These locations do not have layer 2 connectivity between them. They're only connected through, again, a routed WAN type service. So user is using the application, some sort of event occurs where a disaster recovery process is initiated. The application and the server are shut down in the production data center and then booted in the disaster recovery site. So the question now becomes, how does the user know that that application is moved? And how do we get that user's traffic to now hit the disaster recovery site in order to receive service from that application? Remember, we don't have layer 2 connectivity here. So if that user's traffic continues to follow the arrow as shown and enters the production data center, they're not going to be able to find the application. There's no way for the network in the data center there to simply redirect that traffic over to the disaster recovery site. The network in the production site does not know about the MAC address any longer of that virtual machine. So how do we make that happen? So LISP actually has two modes of operation. First, there's extended subnet mode. This mode would be used when there's some sort of layer 2 connectivity between the locations, let's say OTV, where OTV is handling the connectivity between the sites. We've got layer 2 adjacency. We are moving servers from left to right. IP addresses aren't changing. Where LISP would play in that kind of scenario would be where we saw the traffic from the user coming into the data center where the workload no longer is hosted and having to cross that interconnect link. LISP would handle traffic coming into the data center and ensure that it's optimized. LISP would in effect tell the network, hey, this IP address for this server is now in this data center, send your traffic to this data center. Extended subnet mode is really to support those live migrations and data centers that, again, have layer 2 connectivity between them. What we're going to concentrate on, though, is cross subnet mode. This is the mode that would be used when there is no layer 2 connectivity between the sites and when we are moving IP addresses across a routed interconnect. So as we saw in the example, we're moving a server from data center left to data center right, and these sites are interconnected through a routed WAN type of service. And this would be applicable again if the site was, say, a disaster recovery site, or maybe we're moving an application up into the cloud. I think we often think that hot migrations are the default answer. They're the only way that we can get workloads from site to site. Part of my motivation for doing this screencast on this topic was to advocate for the idea that hot migrations are not the only option. There is a good use case for doing cold migrations, and that using technology like LISP and what we're about to look at here enables a very simple design, a very elegant design from the perspective of the user. The user doesn't see anything. They don't have to change how they're working or how they're accessing the application. The network is made intelligent and is made aware about the location of that application and is able to intelligently connect the user to that app. Okay, so let's take a look at the lab here. So this is what I've got set up. We've got 3 locations. We have a branch site where the user is located. We have a production data center in the west, and we have a disaster recovery site in the east. Each of these sites has a router connected to the WAN cloud, which is performing the LISP function. Now, one thing I'm not really going to go into here is all the details about how LISP does what it does. That's not the point of this. This is more of the 10,000 foot view. If you're looking for more details, there is a LISP RFC, which you can reference, and it has many gory details about how this all works. So the basic scenario here is the user is accessing the application that's hosted on the server at 10.10.10.10. That server is going to be cold migrated to the disaster recovery site. And what we're going to look at is how LISP enables the user to continue accessing that server once it's come up in the new location. And we do that without button hooking any traffic through the West data center. The West data center could literally be wiped off the map, burned through the ground, and the user would still be able to access 10.10.10.10 once it's been migrated to the other site. So again, at the 10,000 foot level, the way LISP accomplishes that is rather than performing packet forwarding based on the regular routing table, we actually use a mapping system. So the analogy of LISP is it's kind of like DNS, where we have this distributed database and clients query that database for the mapping between host name and an IP address. Well, in LISP, we have the database, clients, which in this case are actually the routers. The routers do the querying here. Routers query the database, and what they query for is they say, this is the IP or the subnet that I'm trying to get to. Tell me where that subnet lives. And what they get back is what's called a route locator. A route locator would be the WAN IP address for the router that is at the location where that endpoint IP address is hosted. So for example, the user at the branch trying to talk to the server 10.10.10.10, the branch router will query the LISP map resolver and say, I'm trying to reach 10.10.10.10, tell me the location of that IP. The map resolver would return the locator 172.31.0.10. Branch router then encapsulates. So remember, LISP is an overlay, so we're talking about encapsulation here. Branch router encapsulates the original IP frame, IP packet from the user computer in a new packet, addresses that packet to 172.31.0.10, and sends it through the routed infrastructure. The routed infrastructure isn't actually LISP aware, doesn't need to be. It routes the packet normally, hits the West router at the data center. That router is LISP enabled, so it decapsulates that packet and puts the original packet on the wire to go through the data center network. So similar to what I said about OTV, the two end devices here that are talking with each other through the LISP network, they don't actually know LISP is in play there because that original packet is encapsulated and brought through the core of the network. From the end devices, it looks like they're talking to each other just like normal. Obviously, for the reply traffic, the same thing happens. The West router would query the LISP map resolver and ask for the location of 10.30.30.30, and it would get back the IP address 172.31.0.30, encapsulate that packet, route it through the WAN cloud to the branch router. Branch router decapsulates it, puts it on the network at the branch site. Okay, so let's take a look at that in action here. So in the lab, I have the branch routers all set up, all three branch routers. I have my host 10.30.30.30, which I call H1, and then I have my server here, 10, 10, 10, 10. So let's take a look at the branch router. So first thing we want to look at is the routing table. So you notice that there are no routes here for the 10, 10, 10 network. We've got routes for the local subnet at the branch, 10.30.30, and for the WAN interface, 172.30.10 network. LISP does not rely on the traditional routing table. Now you notice something that might look a little odd. We have a static default route here, pinned up to null 0. This is actually how we get traffic into LISP, or how we kind of signal the LISP process in the router here to kick in and do something with traffic that is running through the router. So if we look at this in detail, we look at the data plane for the default route here. We have this check LISP eligibility flag. And what this does is it signals the router when the data plane is forwarding a packet based on this forwarding entry. We actually punt the packet to LISP, and we trigger the LISP control plane to perform that map lookup. So in this case, we have no specific route for the 10.10.10 network. So we're going to match default route. The data plane on the router is going to see that this LISP flag is turned on for this data plane entry, this forwarding entry. That'll trigger the LISP control plane to do that lookup. Now what we can see if we check our lookup cache, so much like DNS, when the router queries the LISP map resolver and gets back some sort of response, the router will cache that entry for a certain period of time, just to facilitate scalability, etc., etc. So currently we have nothing in the cache. The cache is empty. The lab has just been brought up fresh. Nothing's talking to anything else yet. And we can see here we also have a 00 entry. And again, what this is saying is any packet that gets punted to LISP, LISP will check the map cache. The map cache entry here is a negative entry, and we're going to force a map request. So if we flip to our host and we do a ping, so this is the 10.30.30.30 box. We're going to ping the server, and there we go. So we can see here, if anyone caught this, there's actually a packet that was dropped here, and that's on purpose. So when the first map request happens, the initial packet that triggers that map request is actually dropped, and that's just to avoid having to buffer those packets on the router. So imagine a router that's very, very busy, lots of flows going through it, potentially doing many, many map requests per second. Having to buffer all those flows, or those packets, those initial packets, creates a bit of a resourcing problem on the router, and also creates potentially a denial of service situation, where if, let's say, we're buffering X number of packets, it'd be really easy for a malicious actor to forge a bunch of traffic through the router, causing the buffer to fill, in which case legitimate packets are then going to get dropped anyway. So what we do here, we drop these packets indiscriminately, kind of creates a level playing field. So just be aware, if you're playing around with this, it's not a bug, it's actually the way it's supposed to be working. So we look back on the branch router here. Let's look in our cache, and we now have a cache entry for the 10.10.10.10, and we can see that the locator associated with that host is the West data center router, 172.30.10.10. So if we go take a look at the West router, and we look at the map cache over here, you can see we actually have an entry on this side for the branch subnet, with the corresponding route locator. So what happened there is when the server sent that ICMP reply back to the host, the West router was forced to do a map request and find out the location of the 1030.30.30 host. Okay, so flipping back to the topology here. So what we're going to do now is I'm actually going to migrate that 10.10.10.10 server from west site to the east site. Now what's going to happen is because the west router and the east router have been configured in LISP cross subnet mode, as soon as 10.10.10.10 issues a packet on the network in the east data center, the router is going to recognize that, and it's going to recognize that the 10.10.10 network is a network that is being extended over LISP between the sites. And as soon as the east router sees that packet, it's going to register with the mapping system that 10.10.10.10 is now at location 172.31.020. And we're going to see that here in the lab. Okay, so if we go over to the east router for a minute, let's just take a look. So we have no entries for the 10.30.30 network or host, and the routing table very similar. So if we flip back to our host here, we'll just start a ping. And what I'm going to do is perform the migration. And there we go. So we lost a couple packets there, and that's mostly just because the process I'm using to migrate that IP is not all that fast. But now, if we go to the branch router and we look at our map cache again, we can see the location for the 10.10.10.10 host is changed now to the .20, which is the East Data Center. And if we go to the East Data Center, and let's take a look at the map cache here, we have that entry for the 10.30.30 network. So what I just demonstrated there was a successful move of a server from one data center to another across a routed infrastructure, and with very, very fast convergence time, our user, our host, was able to still connect to that application. No changes on the host. The network had the intelligence to direct that user's traffic to the appropriate location. Now, just to prove that this is actually working here, so I'm going to do a constant trace route. So this second hop here, this is the router at the data center. So the .20 is, let's flip over here. So .20 is the east router, .10 is the west router. So right now our traffic is heading from the branch directly to the east router, hitting the server. So what I'm going to do is perform the migration back, and we'll see in real time here how the traffic is redirected. And there we go. So very fast convergence. And again, as I said earlier, we're not hairpinning through one data center. We're not ping-ponging back and forth. The network is sending traffic directly to the site where that application now lives. So in summary, what I've demonstrated here is the ability to perform a cold migration of a server between sites that are connected purely over a layer 3 infrastructure. And I've demonstrated that the network can be intelligent enough to redirect a user's traffic to the proper location where the application is currently being hosted that they're trying to access. Some key use cases for this sort of demonstration would be migrating applications into a disaster recovery site, moving applications into a cloud provider, and even just handling applications in the environment where the requirement to perform hot migrations is not really there. Hot migrations should be considered the Cadillac option and not the default go-to option. Cold migrations do have a valid use, and there are ways to implement them in the environment that are reliable and, most importantly, do not impact the user in any way. For more information on Lisp, please check out packetmischief.ca/tag/DCI, as well as to see the rest of the articles in this series. Please post a comment in the blog or send me a tweet. I'd love to know what you thought of this screencast. And I'd also love to know if you're using Lisp in your environment and what sort of benefits that you've realized from it. Thanks for watching, and we'll see you again next time.